Hello everyone. Now we are going to start topic name as SMF, which we call it a stiffness modification factor. In this topic, first of all, we will look at the theory and the concept, and after understanding this theory and the concept, we will apply this thing in our project. For understanding this topic, we will take a reference of IS 1893 2016, which is an earthquake code, and in this earthquake code we will open the clause number 6.4.3.1. so this is the clause where their definition of a stiffness modification factor has been given, and we will take a reference of another code also, that is IS 16700, which is a tall building code. So in this tall building code of IS 16700, we will open the clause number 7.2, and in this clause number we will open a table number 6. So in the table number 6 we have a modification factor which is given for the uncracked and the cracked, and in this clause IS 1893/2016 of clause number 6.4.3.1 we have a table for giving a modification factor for the column, beam and slab only. Now I will open the code to show you the clause. So this is the code which is IS 193 part 1 2016, and in this code we will look at the clause number 6.4.3.1. so when you will come in the page number 14, so scroll down and come in the page number 14. So this is the page number 14, and this page number 14 you will get a clause that is 6.4.3.1, which is given that for structural analysis the moment of inertia shall be taken as in RCC the and masonry structures 20% of your I gross of column and 35% of I gross of the beams, and in a steel structure I gross of both beam and the columns is given. So let me tell you that in this RCC and masonry structure the modification factor is given 20% of columns and 35% of the beam. So they have not given for the shear wall, also they have not given for the slab also. Now I will open IS 16700 code, which is a tall building code, and here I also will show you that where actually this clause is given for modification factor. So you will open the page number 7. So in the page number 7 you will get a clause that is 7.2 and the table number 6. So let me first of all open the page number 7. So this is the page number 7, and in this page number 7 you will get a clause of 7.2 with the table number 6, and here you will get a clause which is given are cracked RCC section properties. We will look at the both of the reference, that is IS 193 part 1 of clause number 6.4.3.1. also we will look at that IS 16700 tall building with a clause number 7.2 with table number 6. So we will look at two of the reference, or we can say two of the clauses, to understand the stiffness modification factor so that we can apply this thing in our real project. Now before understanding both of the clauses given in IS 193 and IS 16700, we will first of all understand that what actually the stiffness modification factor is and where actually it is applied. So I am going to open the PPT where actually I have given a definition of a stiffness modification factor, and also I will give this PPT in your download section so you can download and study. A stiffness modification factor. So if you look at the word closely, you will find that we are going to modify the stiffness here. So modification factor means to say that we are going to modify the stiffness with some of the factor here. So the stiffness is the structural member here. So if you look at the columns, beams, shear wall, which contribute the stiffness in the building, and in that only we are going to modify with some of the factor, which means that we are going to give the modification factor, which is also known as SMF in the short. So stiffness modification factor. In the topic of SMF, read the first point. So a stiffness is ability to attract moment, shear, axial forces, etc. A stiffer in element, more forces it attracts and more reinforcement we design for. So if you look at here, it tells you about definition of stiffness is that a stiffness is ability to attract moment, shear forces, axial forces and many things like a torsion, like that. So how much stiffer it will be, it will attract that much of it. For explaining this thing, I will take a two beam, one is of bigger depth which I will call it B1, and another beam I will take it with a smaller depth, which I will call it B2. So what will happen in the two of the beam, which is more bigger? Suppose B1 is more bigger, in that case it will attract more moment, more shear forces and all, as compared to B2. So this line tell you about the stiffness is that. So how much stiffer it will be? It will be attract that much of the moment and that much of the shear force, or that much of the axial forces. Now if you look at the next sentence here, considering the crack section, slab is the most cracked. It means it tells you that if you have a slab section, in the slab section we are going to crack it 0.25 here, and the beam we are going to crack 0.35, and finally column and the shear wall we are going to crack, or shear wall, 0.7. So maximum crack we are going to give it in the slab, that is 0.25 here. So the next line is tells you that, so moment from less stiffer member, that is a slab actually is a less stiffer member, will be attracted by the beam and some of the columns. So that's the reason why actually we are giving a maximum crack into the slab, that is 0.25, so that the slab will become a less stiff, and when it will become a less stiff, then the moment and all it will get transferred to the beams and some of the columns there. So that's the reason why actually the slab is giving the maximum crack to the slab here. So if you look at the next sentence here, for considering cracked reinforcement for column and the beam is more than the uncracked section. So it tells you that if you're going to consider the reinforcement here for the cracked section for the columns and the beam, it will be having a more reinforcement than the uncracked section, which will have a modification factor of the 1. For better understanding of this point 1, I will take a prototype model in ETABS to explain you what actually this point tells you. Now let us open the ETABS. So we are in the ETABS, and this is the prototype model I have taken for explanation of a stiffness modification factor here. So we have taken two model. This is the one model and this is the second model. So in the first model we are going to apply SMF, that is a stiffness modification factor. So in the first model I will apply SMF, and in the second model I am not going to apply SMF here. So in the two of the model we will compare two of the result also. So let us apply the stiffness modification factor in the first of the model here, that is the first model. So for applying the stiffness modification factor, first of all I will select my beams here. So in the first I will apply in the beams, then I will apply columns, then slab. So after selecting your all the beams in the first model, I will go to the assign option. In this I will go to the frame option. Here I will find a property modifier option here. In this property modifier option, I am going to modify this moment inertia about 2 axis and moment inertia about 3 axis. So if you look at your codal provision of IS 16700 here, in that you will find for the beams we are going to apply for the factor load as a moment of inertia 0.35 here as a modifier. So let us apply this modifier here. So in the codal provision there is a 0.35 we have to apply. So apply it 0.35 and 0.35. Same thing we have to apply in the columns also. So select all the 4 columns. Go again to assign frame property modifier. In this column we have to give it 0.7. So apply in the moment inertia about 2 axis 0.7, moment inertia about 3 axis, this also will be 0.7. You apply it. Now in the slab we have to apply 0.25. So let us apply in the slab 0.25. So select your slab, go to assign cell. In this you will find a stiffness modification factor here. In this we have to apply in the bending. So you apply it 0.25. 0.25, 0.25 and 0.25. So here I have applied the stiffness modification factor to the slab, to the beams and to the columns also. So anyhow, I will explain these things more detail in upcoming lectures here. But right now I have just applied this to show you that how actually it has been implemented. But in the next upcoming lectures, there we will discuss in very detail that how and why actually we are applying this modification factor in the bending, what the concept and all. We will explain it there in a better way. So after applying here the stiffness modification factor in the first of the model, now let us run it. In the second model, we are not going to apply any SMF here. The analysis has been completed. For the checking the result, you go to any of the plan view, go to the plan view of story 4, and in this plan view, as I told you that we have a two model here, that is model number 1, in which we have applied SMF, and in the model number 2 we have not applied SMF. So in this we have not applied it as a stiffness modification factor. And now let us check the result, what is happening here. So if you look at the beam bending, so for looking that, you go to the display option. Here you will find a force stress diagram. In this you will find a frame, pier and spindle link forces. So you may get this thing directly from here also in the shortcut form, or you may go into display and see that. So in this you select your load case, that is a dead, and you look at the moment 33. Now let us compare two of the model bending moment result. So this is the model number 1 and this is the model number 2. In the model number 1 we have applied the SMF, and in the model number 2 we have not applied the SMF. So I will compare this beam result with this beam result. In this first model number 1A we have applied SMF. Let us see that what actually bending moment we are getting. So we will compare 1, 2, 3, 4, 5, the total 5 beams result here. So I will make a column here of 5, 1, 2, 3, 4, 5. In this 5 there is a two thing. One, we have applied a SMF, and in the second without SMF. So I will write W SMF, which is without a stiffness modification factor. Now let us compare this result. So just take here this beam, select it, do the right click and see the maximum bending moment. So with this SMF with a maximum bending moment, it is 147. So I will write 147 here. Same thing here, I will see for this beam. So this is without a stiffness modification factor, and for this I am getting 157 here. So maximum bending moment I am getting here 157. Now let us do with this beam. So select it and do the right click. So this also is having 157 here. So this is without a stiffness modification factor. Now same thing you do with your beam with which we are given the stiffness modification factor. Do the right click and look at the result. So this is again 147. Now let us look at this result, top of the beam. This is the 101. This is with modification factor. Same thing, compare with this also. So this is 112, 112. Now let us compare the bottom of the beam here result. So this is 101 with modification factor. So 101. Now let us look the downward here beam, and this is 112 without modification factor. Now you can compare your simply supported beam also. So this is the secondary beam. You can compare this also. Do the right click. So we are comparing the secondary beam result here. So with a stiffness modification factor, it is 94, and without modification factor, actually it is 98. Now let us look at these two of the result in detail. So if you look at where we have applied a stiffness modification factor, we are getting a less bending moment. So if you look at the first beam, where we have given here with modification factor, I am getting 147 only. Without modification factor, I am getting 157. So you can see the second beam also same. This value is lesser as compared to this, where we have given a modification factor, the values get reduced. Again this also, where we have given a modification factor and this value get reduced. Here also if you look at, as you compare two of the result, this 101 is smaller as compared to 112. So here also we have given modification factor and this value is less. Even we can see this in the secondary beam also, where we have given a modification factor for secondary beam also, and this also is having a lesser bending moment as compared to without stiffness modification factor. So what actually the conclusion is here, that when we are going to reduce the stiffness, in that case the ability to attract the bending moment, it get reduced. So if you look at the point number 1 in a stiffness modification factor of the PPT, I told you that a stiffness is ability to attract moment, shear, axial forces, etc. Stiffer an element, more forces it get attract, and more reinforcement we design for. So what is happening in the model number 1, when we have given a modification factor, so we have reduced the stiffness for the beams here. So when we have reduced the stiffness of the beam in the model number 1, in that case the ability to attract the moment also got reduced here as compared to the model number 2 here. So in the model number 2 we have not given any modification factor, so the ability of the ability to attract the moment were high in the model number 2 for the beams here. But when we have given a modification factor of 0.35 in the beams, in that case this ability to attract moment got reduced here for the model number 1. So now I will unlock this model, and in this model number 2 I will apply the modification factor here for the beams. I will go to assign frame, I will go to the property modifier, and in this I will apply modification factor 0.35, 0.35, and I will apply it. And for column also I will apply. So for the column I will apply 0.7. Now apply it, close it. So what actually I am making difference here? So in the first model I have applied the modification factor to the slab also. In the second model I have not applied modification factor to the slab. So why actually I am doing this? To explain you the second line of this meaning of the point number 1, that when you are considering the cracked section slab, which is the most cracked, that is a 0.35, and the beam 0.35 and the column 0.7, so in that case some amount from less stiffer member, that is slab, will be attracted by the beams and some of the columns. So we will check that when we are giving a modification factor to the slab, in that case is whether our bending moment it getting transferred to the beams or not. So let us find out this thing. So if you again I will repeat here that in this model number 2 we have not applied a modification factor to the slab, but in the model number 1 we have applied the stiffness modification factor to the slab. Rest is the same. We have applied a modification factor to the beams and the columns also. Now let us run this analysis. Now let us look at the two of the bending moment result. So if you see here, this beam bending moment, I'm just select it and I'm going to do the right click to show you the maximum bending moment. I'm getting 147. So this bending moment remains same how I was getting the previously 147 only. This remains same because we have not done any changes to this model number 1. So modification factor I kept remained same only. I have not done any changes in the model number 1 here. But if you see the bending moment of model number 2, I have given the modification factor to the beams and the columns. I am not given a modification factor to the slab here. But even even after giving a modification factor for the beams and column for the model number 2, we are getting a maximum bending moment for this beam is 91 kilonewton meter here. So what is the reason here? Even we have cracked this, still we are getting a 91 here. The reason why actually we have not given a modification factor for the slab. So when we have not given a stiffness modification factor to the slab number 2, so what is happening? The slab becoming more stiffer here. So when the slab is becoming more stiffer, it is attracting more bending moment and it not let the beams to attract the bending moment more here. So slab becoming more stiffer here. So I told you before also, when we have increased the stiffness of any structural element, this ability to attract the bending moment and shear force will get more there. As compared the two of the model here, the slab we have not given a modification factor. So in the model number 2, slab becoming more stiffer here. So slab is attracting more bending moment as compared to the beam here, and beam if you look at is having a very less bending moment, that is 91, as compared to the model number 1 when we have given a modification factor through this. So as you can just see here, point number 1 of the line third, so some moment from less stiff member, that is a slab, will attract by the beams. So when you have given a modification factor, in that case what will happen, the slab will get less stiff and it will the bending moment will attract by the beams and the columns here. Now I think that you can clearly understand this point number 1 with this type of the prototype model which I have explained you. Now if you look at the second point, that building in some element are stiffer and other are less, so that they attract different amount of forces and depending upon their stiffness. The second reason why actually we have to give it modification factor is very common to the first reason only. So this also I have explained you that if you look at the building, they are made of some element like slab, columns and the beams. So which is more stiffer will attract more bending moment. So the different amount of forces it will be attracted by of the element here. So we are going to reduce the stiffness by giving a modification factor so that it can actually transfer the beams moment very easily. If you look at the second reason here, that applied loading on building produce internal forces. These internal forces like flexural, shear, torsion, axial forces result in compression or tension in concrete fibers. Concrete is stronger in the compression, but it is not good in tension, as little about 10% of its compressive strength. At this limit, the concrete cracks and reduce the area and stiffness. So the third reason tells you about that when you applied, suppose this is my beam or any slab I have, when you applied a loading here. So due to the loading, what will happen? There will be a creation of compression and the tension. As you know that tension is very less in the concrete. We have only 0.7 root FCK only as a tensile strength of your concrete. Also we can call it the rupture strength, or generally we can call it tensile strength also. So very less we have a tensile strength of the concrete here. So what will happen when the concrete is weak in tension? In that cases, what will happen? There will be that will lead to the crack here. So that's the reason why actually we are going to apply a stiffness modification factor to the slab, to the beams, to the columns and to the shear wall also. So this is the third reason where we applied a modification factor, because concrete is weak in tension and it takes only 0.7 root FCK only. That is a rupture strength, or we can call it tensile strength also of the concrete. So I think the theory point is very clear to that first point also, second point also and third point also, why we use the stiffness modification factor to the building, or we can say structure element. If you look at the fourth point also, it is also very common to the first point only. As the stiffness reduced, so that the moment attracting ability, some of the moment which was present in this section, for example beams, goes to the other areas which are not get cracked for the columns, this resulting of the stiffness in the whole structure, and that leads to the redistribution of the moment. So what I have explained you in the first point, that there will be redistribution of the moment when you give the modification factor here. So the fourth region is very common to the first region only. Why actually we give the stiffness modification factor to the structure element, that is a beam, slab, shear wall and the column. So this is the end of the part number 1 of modification factor. In the part number 2 we will look at more the codal provision, also we will look at that implementation also.